Now I have an inductor of some magnitude L. Hey, you know what? The voltage across the power supply minus the voltage across the inductor is going to be equal to 0. Kirchhoff. Oh, drop the delta. All right, so the voltage across the inductor is going to be, well, the voltage across the power supply, which we established over there, epsilon cosine omega t plus phi. But the voltage across an inductor, I know we derived it in class, we didn't do much with it. This is the time that I guess we used it when we were looking at the LC circuit. Took a charged capacitor and then it oscillated back and forth. But this is going to be L, the inductance, times di dt. Or di dt is equal to, when we're in math, epsilon over L cosine omega t plus phi. So I equals, let's bring back those calc 1/2 skills.
E over L omega sine parentheses stuff.
Is that what you're doing? You're taking a derivative. We need an antiderivative.
Oh,
So epsilon over L omega,
Epsilon over L omega.
then sine function.
Did we take an antiderivative last time too, or we did
No.
derivative?
We did derivative last time.
Yeah, because this is different. This one.
Yes, yeah. So looking at that, I know that my magnitude of my current is going to be epsilon over L omega. If I put it into Ohm's law form, I get epsilon is equal to I times L omega. And of course, we can't get away with not calling this something. And this is, someone would take a shot at what it's called. Go for it, Paul.
I don't know.
Start
The
with
last one was
capacitance still.
No, it's not, we're not dealing with capacitor,
Conductive.
loads and inductor.
conductive reactive.
react.
No, Paul,
Conductive reactive.
you say conductive?
Conductive.
No, this is the inductor, not an inductor.
Inductive
reactance.
Inductive reactance. So our inductive reactance has the formula of omega L. I know that epsilon is going to be equal to, this technically equals capacitor. So we have these Ohm's law analogs. And if we look at our functions here, see, cosine, our voltage is a cosine curve. Our current is a sine curve.
The amplitude cosine stuff, that was voltage is what we started with, and then we
Yeah.
got to current from there.
Yes.
Is that like the area under the curve or between the two curves or something?
It would be the area, well, I mean, we're doing an integral, so it's the area under the voltage curve.
Under the voltage curve, okay.
Times a constant. All right, so that is voltage. And our current. So as I'm going, increasing in time, I'm going to peak for my voltage, and then I'm going to peak for the current. And so we now have the last component that we want. So for an inductor, the voltage plus an inductor leads the current. Not a C there, it should be an L by pi So, you're in a test, or quiz, or doing a master set, and you're thinking, all right, wait, capacitance, inductance, I know one leads, one lags, which one is it? I had a little rhyme that worked for me for a while. But then a student came up and said that she had heard something that worked actually even better. So first off, for you future electrical engineers, your ancestors, I think they just got lazy. But that's just mine. All right, so when this was all being typeset, I mean, how many printers are gonna have an epsilon? So what they decided to do, instead of doing epsilons, they decided, you know, we're just gonna go capital E for voltage instead of EMF. And so the electrical engineers, at least my experience with electrical engineering textbooks, is they use the capital E for voltage. And that comes from the epsilon, which they didn't figure out how to print properly. So, in what I had come up with, and if it works for you, great, and if not, is that for a capacitor, I comes first, so I before E when talking about C. However, the student told me about Eli the Iceman. So when we're talking about inductors, E comes first. When we're talking about capacitors, I comes first. And Eli the Iceman actually does seem to work better. At least I hear more students making reference to it. Questions to hear?
How come we didn't mess with inductors and DC circuits?
I guess it was not my mood. There's nothing wrong with it, I mean,
There's stuff that happens with inductors and DC circuits like too?
inductors, my experience, inductors show up more with AC circuits, and I don't know why.
Okay.
Childhood scars, as usual. All right, so now, an actual problem. I have a AC power supply, I have a capacitor, and I have a resistor. So this would be an AC RC circuit, RC series circuit. And what I want to do is come out with what is known as the impedance. Now, impedance, a word I have not used yet. Notice we have an Ohm's law variation, well, it's pretty much Ohm's law variation for capacitors and for inductors. We actually have an Ohm's law variation for circuits, for AC circuits. And it's that epsilon equals IZ. The Z here is impedance. And it is pronounced impedance, it is not pronounced impedance. Now, if you're looking at a textbook very quickly, you will see formulas for impedance. But I warn you, there's no set. For capacitive reactance, I have a formula. For inductive reactance, I have a formula. For impedance, it is circuit specific. And there are a number of problems where what they ask you to do is find the impedance, find the formula for the impedance. So what we're going to do is find the formula for the impedance here. We're going to do this, there's more than one way of doing it. We're going to do this using phasors.
Invoking Star Trek here?
Is the phasor in Star Trek spelled with an E?
Probably. Maybe even a Z, I don't know.
This is, come on, this is the most advanced physics class we have here. Surely somebody knows.
Oh, so Star Trek.
Probably at PHAZER. ZR, I bet.
I don't think it's a Z.
Sure.
I feel very confident it's not a Z.
You asked us, so.
I also nerd brains there. But. All right, a phasor. Think of a phasor as it's like a vector. It's similar to a vector, except it spins around a central axis. So this would be an example of a phasor. It's basically pinned at the origin and it spins around counterclockwise. And the phasor represents the voltage or current of one of the components. So in a phasor diagram, we're going to have a voltage phasor and a current phasor for each component. I have 3 components here, so I'm going to have 6 phasors. This is going to spin around with an angular speed of omega. The same omega that shows up in our formulas over there. So the angular frequency of the oscillations of the power supply would match the angular speed of the arrow going around counterclockwise. So I'm going to start out with, or when you're doing phasor diagram versions of it, you look at this and you say, all right, is there anything common to everything here? Do all the components have the same voltage, or do all the components have the same current? You didn't sound sure.
I'm pretty
Current.
There we go. That's yes, it's series. Whatever current, think of in a DC circuit, whatever current flows out of here has to flow across that, has to flow across that. So the current phasor is the same for all 3 components. And so I'm going to draw it. Now, where you draw it is somewhat arbitrary. I tend to like somewhere around 30 degrees. But I'm going to label this by the magnitude. So that's I sub C, which is equal to I sub R, which is equal to I sub power supply. So we have 3 phasors done already. We just have to figure out the other 3. For the resistor, I know that the current is in phase with the voltage. Well, this is my current for the resistor. If the voltage phasor is in phase with it, that means it's on top of it. They're in exactly the same position. They are in phase. Now, whether the green arrow should be drawn longer than the blue arrow, they're on 2 different scales. The second one I draw is the shorter one. That's just the way I do it. So this is voltage for the resistor. And actually, I'm going to write that up here because I know where we're heading. For the capacitor, its voltage, well, current comes first. So for the capacitor, that's supposed to be a right angle there. Here's my voltage for the capacitor. And for the power supply, well, if I'm looking at this point and this point, whatever voltage gain I have going that way, voltage gain or loss I have that way, whatever my voltage is across there, I have the same going across there. In other words, if I add up these 2 voltage phasors, I should have the voltage phasor for the power supply. It's going to sum up around there, so there's my S1. That's my phasor diagram. Now it's not loose-sided backward tools trying to find the impedance. Any questions before we take the next step and actually do equations?
Can you explain what a phasor is one more time?
It is a representation of a typically current or voltage of a component in an AC circuit.
Any AC circuit?
Yeah. Are phasors always the easiest way of solving them? Depends. Well, at some point I'll show you an alternative
It's
method.
like a graphical representation of
Yeah, I think that's legitimate.
Okay.
It is similar to a vector in the way you do addition, but it is fixed at the tail and rotates counterclockwise. So imagine that these arrows are all spinning around.
Oh. Okay.
Why did you pick for the VC when you made it? You made it a right angle.
Because we established that all the currents are the same, because it's a series. And I know for a capacitor, the current leads. So if these things are moving around, well, actually from your point of view, if these are moving around like that, the current's gonna be coming first. And so the voltage lags by 90 degrees, or the current leads by 90 degrees.
Is that true for every phase diagram, phasor diagram?
For a particular component, so for a specific capacitor, then the current phasor will lead that voltage across that capacitor by 90 degrees.
Okay.
Yeah, that's one of the set rules.
Is that only when they're in series though?
No,
Okay, so just series, parallel, whatever.
Yep.
Yeah. Okay.
don't worry, we'll see a parallel. In case you were worried, I don't want you, if we don't get to it today, I don't want you leaving here and then crying yourself to sleep because we didn't get to it.
We're all very worried.
I know. All right, let's do some math. More math. When I added these are at a 90-degree angle to each other, and that is the same as this. This length here represents VC, this represents VR. That is a right angle there. It's just Pythagorean theorem. I know that the epsilon squared is just equal to VC squared plus VR squared. That's supposed to be a V. There we go. They're all capitals because these represent the magnitudes, the amplitudes. Plugging in our Ohm's law variations of it, this is equal to IZ. So I power supply Z squared is equal to I capacitor X sub C squared plus I resistor X sub R squared. All my currents are the same in this problem, so I can just divide them out. And I'm left with Z squared equals X sub C squared plus X sub R squared. Oh. What boneheaded mistake did I just make?
Oh, you didn't factor it, not factor, but
Distribute the exponent.
No, I mean, I just skipped that step.
Oh.
That was not the boneheaded mistake. I have a symbol down here for which is not really defined.
Z?
X sub R. It's just R. There is no X sub R.
What, can you tell me what Z represents?
Z is the impedance. It's sort of an AC analog of the equivalent resistance of a circuit. Yeah.
So where did the I go? Did you just cancel
Oh.
it? Cancel out?
So all the I's are the same. So this would be I, whichever symbol we would use, that's I squared, Z squared is equal to I sub C squared, X sub C squared plus I sub R squared, R squared, but all the I's are the same, so we can factor, cancel it.
Oh.
And so that's where the I's went.
And if they weren't the same, you'd leave them there at the end.
Yes. Then when we get to parallel, they will not be the same. All right, so Z is equal to the square root of X sub C squared plus R squared. But X sub C we have a formula for, so that's the square root of 1 over omega C squared plus R squared. And that is the impedance of the AC RC series circuit.
X sub C, that's 1 over omega C.
Yes,
Is that the angular, something over the capacitor?
oh, omega,
Yes.
that is the angular frequency of the power supply.
Across the capacitor?
Yeah, this is oscillating back and forth at some frequency. Everything's gonna have that same frequency.
Okay.
So it's, oh, I erased it. It's that same omega there.
You said it was, say it one more time, it was, angular,
Frequency.
angular frequency. For the X sub C.
Yeah, that omega is the same as that omega, which is the same as the angular frequency of the power supply.
Conceptually, what is impedance?
Valeria, you wanna take that one?
Impedance.
It is a measure of it's basically the AC analog of equivalent resistance.
But, see, that's the thing that I don't understand, what is the AC analog?
AC, alternating current. So it's very similar to the equivalent resistance you would have in DC circuit. DC circuit, it would just ask for what's the equivalent resistance.
Analog.
Is it always changing or something though, because it's
Yeah.
alternating current, therefore the equivalent resistance or impedance is always going to be moving around too, or?
No, the impedance, once you have the formula, it will be a set number.
So the value of the current, if it's alternating current, the values of the actual current's not going to change, like